Adam Ward here. This is video 2 of 4 in our pipe flow potpourri, so finishing up things like major and minor losses. In this video, we're going to take a look at what happens if we have a non-circular duct, and we'll also look at systems of pipes, either in series or in parallel to one another. Alright, so non-circular ducts in one slide. So what happens if we don't have a round pipe? For example, if you are working in HVAC systems, so ductwork that moves air around in a home, for example, these are often rectangular. And so think that we've got a rectangular section of a pipe with a width of L, a height of W there, and it's moving flow in and out of the screen that you're looking at now. If we want to deal with that, we actually don't have a solution right now because everything we've done has been in terms of diameter. Fortunately for us, there's a concept called a hydraulic diameter. And so what this is doing is converting different shapes into their equivalent circular geometry. And so what we would calculate for our hydraulic diameter is 4 times the area divided by the wetted perimeter. And we'll look at what that means on this slide. So for example, for this problem, the area 4 maps over directly, and then the area of that rectangle that I've drawn is length times width. And then in the denominator, the wetted perimeter, this is trying to describe what is the length of the wall of that duct that's in contact with the fluid. And so for example, if this thing is flowing full, then the wetted perimeter that we're trying to calculate is the entire outer surface of the pipe. So I've got 2L plus 2W because we have L on the top and bottom and a width on the left and right. So 2 L's plus 2 W's. Now, what if we had a rectangular or a square pipe, but it wasn't flowing full? Right, so it's got some width L and some height of water H. We still use that same approach, and the area is perhaps the more straightforward. 4 is still a 4, area is still the length times the height. But for the wetted perimeter now, you'll notice that what I've included is the length to make sure we're covering the bottom of the pipe, plus height on both sides. So length plus 2H to get that wetted perimeter. This doesn't just work for rectangles, this works for all shapes. You would use the same approach if it was an ellipse or a triangular pipe or, I don't know, something more creative or oddly shaped than that. So non-circular ducts, your strategy is convert the geometry of the problem into a hydraulic diameter and then work the problem as you would have historically done so. That hydraulic diameter can go into things like Reynolds number. It can be used in epsilon over diameter on the Moody diagram. So that's our strategy. The other new topic to introduce to you here, the last in our pipe potpourri, is what if pipes are operating in series or in parallel? And so for example, pipes in series, we've got a flow moving from left to right on the screen. So through pipe A into pipe B from point 1 to point 2. Conservation of mass, you should be able to convince yourself that however much flow is moving through pipe A, that same amount of flow, that same mass rate must be moving through pipe B. So QA and QB are the same. However, what is not necessarily the same is the losses. So if you want to know the head loss from 1 to 2, it's the head loss in section A plus the head loss in section B. That would be how we might calculate things like the major losses here. So for example, oops, I thought I had something more written. So the losses are additive here. So if you wanted to know the total head loss, you could do the friction factor in A, length of A over diameter A, velocity in A squared over 2G, and add to that all of those same quantities for pipe section B, VB squared over 2G. Right. So everything that you've already done, just adding it to itself again. Right? Major loss plus major loss. All right. The other condition we might have is pipes in parallel. So for whatever reason, our flow diverges into two or more parallel threads of pipe that later converge together. And now in this case, fluid does something pretty interesting. The flow rate does not have to be equal. So the total amount of flow, whatever was at point 1 and whatever is at point 2, those have to be equal. Mass rate in has to equal mass rate out. But the way that it splits, the way that it divides between A and B does not have to be equal. And so in most cases, QA and QB will not be identical. It's possible for them to be identical, but it's typically not the case. Now, if those flows are different, what's interestingly the same is that flow will separate so that the head loss balances. In other words, it's no easier to move through pipe A than it is to move through pipe B, or the same total amount of energy is getting lost on both of those pathways. So the head loss through each of those parallel sections of pipe is going to be identical. Or in other words, major losses through pipe A are going to equal major losses through pipe B. They can be made of a different material, they can be a different diameter, they can be substantially different lengths, and the flow will equalize or equilibrate so that the same head loss occurs through both of those sections of pipe. So for pipes in series or pipes in parallel, what you want to do is quickly remind yourself what's equal between the pipes. So pipes in series have equal flow, pipes in parallel have equal head loss. If you know what's equal, the opposite or the other piece of the problem is the thing that is not equal, and you can calculate it. So following up on this, we're going to do 2 more videos, one example on pipes in parallel and one on minor losses. Stick with me and I will see you soon.